EES, which is pronounced EASE, is an acronym for Engineering Equation Solver. In the last two videos, we talked about setting the unit system and accessing properties for real fluids. In this video, we'll do a simple example that just illustrates how we can use these properties to solve a real engineering problem. So this is a vapor compression cycle schematic. The working fluid in this cycle is ammonia, and it changes state as it circulates through a compressor, a condenser, a throttling valve, and an evaporator. The cycle is providing refrigeration to a low temperature reservoir at Tc equals 260 Kelvin, and it rejects heat here in the condenser to a high temperature reservoir at Th equals 320 Kelvin. So first we're going to set up the unit system using the $unit system directive, and then we'll enter the inputs. And you should note here that the fluid name is entered as a string variable $. We're going to assume that the refrigerant leaves the condenser at state 4 as saturated liquid, so it has quality 0, and it's at the heat rejection temperature Th. So these two intensive properties fix state 4, and that allows the specific entropy, pressure, specific enthalpy, whatever else I want to be determined using the property functions. So we're going to use here the property functions entropy, pressure, and enthalpy, and the indicators will be T equals for temperature and X equals for quality. So if we solve at this point, you're going to see that the fourth element of each array has been filled in, and it's worth setting the units of each of these variables and verifying that we don't have any unit issues or any other problems before we move on. So coming back to the cycle now, the refrigerant leaves the evaporator at state 2, and we're going to assume that it's saturated vapor, so it has quality 1, and that it's at the refrigeration temperature Tc. And again, these two intensive properties will fix the state, so that allows us to compute any other property we want. In this case, we'll use the functions entropy, pressure, and enthalpy to get those properties at this state. So the fluid leaving the condenser here at state 4 is expanded to state 1 through a throttling valve, and we'll assume that throttling valve is isenthalpic, and so the specific enthalpy at states 1 and 4 are equal. And if we assume there's no pressure loss in the evaporator, then the pressures at states 1 and 2 are equal. So knowing the enthalpy and the pressure, that fixes state 1, and we can then use the indicators H equals and P equals to get any other property we want. In this case, we're getting entropy and temperature. The fluid leaving the evaporator is compressed to state 3 in a compressor, and we're going to assume the compressor is both reversible and adiabatic, so therefore the specific entropy at states 3 and 2 must be equal. And if we assume there's no pressure loss in the condenser, then the pressures at states 3 and 4 must be equal. So entropy and pressure then fix state 3, and we can use the indicators S equals and P equals to get any other property we want. In this case, we'll use the functions enthalpy and temperature to get the enthalpy and temperature at this location. So solving at this point then provides all the properties at each state, and you can see they're conveniently organized in this array. Section 4.6 of Mastering Ease will show how properties in an arrays table like this can be used to create property plots on which cycle state points are overlaid. So for example, we might be able to make a pH diagram and show exactly where the cycle state points are on that pH diagram. Finally, we'll finish the problem by doing energy balances on the condenser, evaporator, and a compressor, and we'll do this on a per unit mass basis, so that gives us the rate of heat transfer from the condenser into the evaporator, as well as the rate of work transfer to the compressor. And then the coefficient of performance of a refrigeration cycle is just the ratio of the evaporator heat transfer to the compressor power. And if we solve at this point, we find that the COP is 3.37. One thing to note is that because we entered the fluid name using a string, it becomes really easy to examine the use of other refrigerants. So I can change the string to R410A and compute the COP, or I could change the string to R134A and look at how that cycle performs. It's also easy to make plots using a parametric table. So here I'm going to show how COP varies with the refrigeration temperature Tc. So this is one of a series of tutorials that's meant to describe the operation of the EASE software. If you'd like to get more information about EASE, obtain the software, or access more of these tutorials, please go to the website fchart.com. These tutorials are excerpted from the book Mastering EASE, which can also be obtained from the FChart website.